Hello guys, good evening and welcome.
Good
Uh,
evening.
yeah, so can I just confirm, is my audio clear? Any background noises?
Yes, sir, all clear.
Clear, right? So, uh, great. Okay, so we'll slowly begin. I think let people, others also join slowly, but we'll just start our discussion for today. Primarily, today we will focus on week 7. I know things are going a bit fast. You you may be in week 5 or week 6, but we should all pace up a bit because next to next week is quiz 2. I hope all of you know that. So the date of quiz 2 won't change, right? So therefore, we should speed up. Okay, so we'll have most of our discussion on week 7 and we'll try to finish week 7. Week 7 is like 4-year series, majorly on 4-year series and introduction to 4-year series. Right, so we will, I think professor has given some background. He spent some time on giving you the math behind how exactly that 4-year series expansion has come and how to compute the inner product spaces and everything he bought in and how to compute this 4-year coefficients. Right, so we'll not be doing that extensively. Rather, I will show you the expressions and then we will move on to solving problems. That is what we need, right? Ultimately. So we'll have little bit discussion on the 4-year series and its representation and the expressions for how to compute 4-year series coefficients. And then we will move on solving problems. And then at last, I will also point out the properties of 4-year series, which are really important, right? So we can't always sit and substitute, use the formula, substitute the values and solve it, right? So we should know techniques which speeds up our calculations and those techniques are using these properties. Okay, so we'll see them everything. Okay, so unfortunately, I don't have any slides for this. Rather, I will just write them. Okay, so if you are not able to understand the writing, just let me know. Okay, so I'll write it. I'll try to write it better. All right, so let's begin. Let's begin with the periodic signals. So let's revisit this periodic signals because we primarily compute 4-year series representations for this periodic signals. Right, so let's revisit this. And we all know what are periodic signals. Any signal when shifted by some amount, right, x of t plus some amount, I should get back my same signal. Right, so for all t. If this happens, such a signal is called periodic signal. Right? Just a second. I'll just turn this on. And this t, the smallest such possible t, is called fundamental period. And the omega naught, which is 2 pi by this capital T, is fundamental frequency. Right, so I know we would have seen this earlier also. So why is it relevant here? Because the idea of 4-year series lies behind these things. So what we are going to do is uh, we are going to express our periodic signals, any periodic signal, you give me any periodic signal, I will express that periodic signal as sum of harmonics of sinusoids or sum of phasors, in other words. Okay, so that's the core idea of Fourier series. I will write that down too. But let's understand this phasors once more. Okay, so let's revisit this phasors once again. So we know e power j omega naught t, right? So this is a sinusoid, right? Complex sinusoid. Soid at frequency omega naught, right? And we are going to introduce one more phasor kind of thing, which is e power j k omega naught t. Like you are taking the power of the complex sinusoid by k, you will get e power j k omega naught t, right? So that is called the kth harmonic sinusoid. Okay, so and we are going to use this kth harmonic sinusoids, so different values of k, and we are going to express any given periodic signal as, we call it as, technical term is linear superposition. Like we are going to express any periodic signal as a sum of these harmonic sinusoids, and that is the core idea of Fourier series. Right, so earlier you would have seen Taylor series, right? So in math 1 you would have studied Taylor series. So Taylor series is one way of expressing a function, right? So e power x, we will write it as the Taylor series expansion as 1 plus x square by 2 factorial plus, right? So we are expressing some function e power x as sum of polynomials, right? In the same way, the Fourier series is expressing some periodic signal as sum of harmonic sinusoids. So that's the core idea, right? So the main idea of Fourier series is any periodic signal can be written as a linear superposition. So linear superposition is nothing but the summation of some coefficients multiplied with this harmonics of harmonic sinusoids. Right, so this is the core idea, and you can see the terms, the linear superposition. You have to understand what linear superposition is. Right, so linear superposition is basically some alpha times some function plus beta times some other function plus gamma times some other function. So it's linearly summed up. So there will be a scaling factor plus there will be the summation. Okay. So in mathematical expressions, this is how it is. You give me any x of t which is periodic, I can express that as summation of this harmonic sinusoids, kth harmonic sinusoids with some coefficients, where k goes from minus infinite to plus infinite. Okay, so these a k's, which are the coefficients of kth harmonic sinusoids, are called the Fourier coefficients. From the name itself, you can see, right? So they are just the coefficients of each harmonic sinusoid. So how much weight each harmonic has, those are the coefficients. So these AKs are Fourier coefficients, right? And this expression is called synthesis equation. Okay, so x of t, you express it as summation k is equals to minus infinite to plus infinite ak times e power j k omega naught t. And all we need is to find out this ak. So our ultimate goal, if somebody asks you, find the Fourier series representation, that means you are not behind of this. It is already e power j k omega naught. So you should know omega naught, but you are not majorly behind of this. So our primary goal should be computing these AKs, which are the Fourier coefficients. If you have the Fourier coefficients, all the Fourier coefficients, you can express any periodic signal as Fourier series. So our primary goal should always be computing Fourier coefficients. And also a chota goal or small goal is to compute omega naught. So this should be done first. Then only you can come back and compute Fourier series coefficients. Okay, so we compute omega naught also. So that's there, that we have to do anyway. But this is our primary goal. Okay. So since I mentioned that's the primary goal, we should have some explicit expression, right? So can we have some formula which we can just substitute and get it? And ultimately, yes. So there is a lot of math, inner product spaces behind this. And that is why we have stated that orthogonality between two signals and the two harmonics when multiplied together, right? So this we have seen, right? With the different frequencies, it will always be zero. Therefore, any two harmonics inner product will always be zero if they have different frequencies. All these things, we use all these ideas and ultimately we arrive to this very nice formula to compute Fourier series coefficients. Right, so this AK can be computed using this. Right, so x of t e power minus jk omega naught t dt. And this AK is coming from here. So we just take inner product between x of t, right, and this e power jk omega naught t. So if you take inner product between these two, only the kth term will survive. Everything else will get, since this is an inner product, everything else will have different frequencies, and inner product between different frequencies with omega naught, everything will go to zero except the kth. Okay, so that's the idea. If you want more details, you can take detailed look at the lectures. So professor has explained it very nicely. Okay, so what we do is we will take this, and this equation is called the analysis equation. So the above one is called synthesis equation and the below one is called analysis equation. This is just for your information. I am telling you, it's not that important. But if you are reading any textbooks related to signals and systems, you will often encounter these terms. So synthesis equation, analysis equation. So for that, you should know what exactly they are referring to, right? So that is why I'm giving you this. Okay. So okay, so let me just hold on for a minute and ask any doubts till now. I know this is very basic, but still,
No, sir.
no. Are we happy? So if we can find AKs from this synthesis equation, so if you can represent your x of t as summation of this harmonic sinusoids, then you don't need to use this below formula, this analysis equation. Right? I will show you examples. So if you don't need this analysis equation at all. Right? If you are not able to express it in that way, then you have a nice formula which you can use and compute the Fourier series coefficient. Okay, so we'll see some examples now. And then we'll get the sense of how to use, which formula to use, or do always I have to go behind the formula, or some common sense can work. Okay, so let's see some examples. The first example we'll see is x of t being cos 2 pi t. Okay, so we all know cos 2 pi t is a periodic signal, right? So it's a periodic signal. Periodic signal with period, fundamental period. Can anyone tell me t and omega naught?
T is 1 and omega
T,
naught is equal to 2 pi.
correct. So t will be 1 and omega naught will be 2 pi by t, which is 2 pi. So here also this capital T is I forgot to mention this capital T is the fundamental time period. Okay. So this we discussed above also. So capital T is fundamental period of the signal x of t. Okay. Fundamental period. Okay, so here in this particular example, capital T is 1, omega naught is 2 pi. So we computed omega naught and we'll just keep it aside. Okay. I will tell you where it will be useful. Now, should we go and use this analysis equation, or can I express this cos 2 pi t as sum of phasors? So can we write this some cos theta as sum of phasors? Did we encounter these kind of expressions or equations anytime? So did you guys know this thing? Cos theta can be expressed as e power j theta plus e power minus j theta by 2. How many of you know this?
Yes, sir.
Yes, right?
Yes, yes, sir.
Okay.
Yes.
Yeah, great. So then we'll use the same idea, right? So here, instead of theta, we have 2 pi t. That's it. So now I can write this as 1 by 2, or let's write it like this, e power j. So instead of theta, I'm going to substitute 2 pi t, right? So e power j 2 pi t plus e power minus j 2 pi t whole divided by 2. Right, so this is what we have. So this I can simplify it as half into e power j 2 pi t plus half into e power minus j 2 pi t. Right, so now you just have to compare this with this. Right, so for that you see this expression e power j k omega naught t. So for finding k, we will just separate out j, omega naught and t, and whatever is left, that will be k in the power, right? So here we know that omega naught is 2 pi. So that means I have to separate out j, 2 pi and t, and whatever is left, that will be k, right? In the first expression, you see j, 2 pi and t, right? So if I exclude all three, what is left?
1
Into 1. Correct.
into 1, yes.
correct? So in the second expression, you see t, 2 pi and j. So if I
Maybe
exclude
minus
these
1.
three,
minus 1.
Minus
minus
1.
1. Very good. So we will just round that off. So our required is 1 and minus 1. So those will be our Fourier coefficients. So this will be A1, this will be A minus 1. And what about the rest? Everything will be? What about the A0, A2, A minus 2, A minus 3, A3? All will be zeros, no? Right? So A1, therefore the Fourier coefficients are A1 is equals to A minus 1 is equals to half, and AK will be 0 for K not equals to plus or minus 1. So these are the Fourier coefficients for this first example. And remember, we didn't use any formula. We didn't use this analysis equation. Right? So all we did is to express this cos 2 pi t as sum of phasors. That's it. Sum of phasors with different case. Okay? So that way, you don't have to always use this analysis equation to find the Fourier coefficients. Rather, you can express it in this way also. So let's do one more just to get some better understanding. Let's say x of t is 1 plus sine 2 pi t. Okay. So 1 plus sine 2 pi t is also periodic signal. Correct?
Yes, sir.
Yeah. And the period is period will be
2.
Pi.
2 pi. See, adding 1, what will it do to the signal?
Sir, 1, sir. T is equals to 1 and W naught, like omega naught is equals to 2 pi.
Correct. So adding 1 is like adding a DC value, right? Constant value. It will just shift your signal
Option.
to the amplitude, the magnitude will change. That's it. The period will not change, right? So whatever the period is there for cos 2 pi t or sin 2 pi t, that will be the period. So if you are adding 1 or some constant value, it will just shift the magnitude, not on the time axis. It will just shift on the magnitude axis or y axis, right? So t will be 1 and omega naught is 2 pi again. Okay. So now what? So this will be 1 plus, how can I express sine 2 pi t? Again, cos theta can be expressed like this. Sine theta can be expressed as
A की power j theta minus A की power minus j theta divided by 2.
2j.
divided by
2j.
2J.
2j. Correct.
J.
So there will be j. So we'll use again, instead of theta, we'll use 2 pi t. That's it. So we'll have 1 by 2j into e power j 2 pi t, and there will be 1 plus 1 by, sorry, minus 1 by 2j into e power j 2 pi t, and there will be minus 1. Right? And here 1 also. So here I don't have any e power something. Right? So what can I, so I need in this expression, no? Something like e power jk omega naught t, no? So what does
A
this
to the power
DC value
j.
correspond to? Yeah, exactly. So this 1 into, I can write, I can bring in this j 2 pi t and 0. Right? and then the other one, the next two terms will be the same. The other two terms are the same, and here you can clearly see this corresponds to k is equals to 0, this corresponds to k is equals to 1, and this corresponds to k is equals to minus 1. So therefore, we only have three non-zero Fourier series coefficients, which are a0, which is 1, a1, which is 1 by 2j, and a2, which is minus 1 by 2j. Right? So there is minus also here. And all other AKs are 0 for k not equals to 0 and plus or minus 1.
Sir, A minus.
A
Sorry?
minus 1, sir.
Oh,
A
sorry,
A
minus
sorry,
1.
minus
sorry,
one.
sorry.
Minus one.
Yeah, sorry. So this will be a minus 1. Yeah, thanks for pointing it out. Okay. All right, nice. I think let's do. Okay, maybe I will give this as an exercise to you guys. You can try it out. Okay. So let's not spend too much time on this. So let's say you have sine 2 pi t plus cos 4 pi t. Okay, so something like sum of two periodic sequences will also be periodic. Right. So first of all, compute the time period t and then omega naught, and then you know how to
Sir,
express
it will
this.
be LCM.
Sorry.
LCM. So the
LCM.
time period should be the LCM.
Hmm. Correct. Whatever you said is correct. And you can express this sine 2 pi t as in terms of sum of phasors, and cos 4 pi t also you can express it that way, and then you'll get some nice summation, more terms in your expression, and identify for what case k. These are non-zero, right? So identify the k values, and corresponding coefficients will be the a case. And whichever AK is not there, those all will be 0. Right, so it's a nice exercise. You all can try, not now, or if you can try it parallel also. I don't mind. Okay, so maybe I will put this as an exercise. You can start a discourse post, or maybe in GSpace you can answer. All right, so these are some problems where you don't need that analysis equation that I mentioned, right? That 1 by t integral minus t by 2 to t by 2 x of t into e power minus j k omega not t into dt. Right? You don't have to compute those integrals. Let's see one nice example where this integral plays to understand this integral thing very, very clearly. And I think most of the profs, or wherever you go, when you take signals and systems as a course, and when Fourier series chapter comes, this particular example nobody will forget to mention. Okay, so the example, I think most of you would have already guessed it. The rectangular pulse, right? Pulse train, which is this. Okay, so this will be periodic with period t. Okay, so let's say this is capital T. So this is symmetric around y axis, so it will be minus t by 2 and this will be plus t by 2. So the overall, the total length will be capital T. And this also I would like to discuss the general version. Let's say this is minus t1, some t1, and this is t1. Okay, so this is generalized rectangular pulse with period capital T, and in that period it will be non-zero from minus t1 to plus t. Okay, it's not half of t by 2. Okay, be very mindful. T1 is not t by 4. Okay, it can be t by 4, but I'm just giving in general some t1. It need not be necessarily t by 4. Okay, so for this, if we were asked to compute the Fourier series coefficients. Okay, so for that, let's write down this fundamental time period is t. So omega naught will be 2 pi by capital D. Okay, so that we have. And now we can't now express, right? So taking x of t and looking at closely, and we can't express it in terms of summations. So what we do is we will use the formula. Okay, so the formula is ak from minus t by 2 to plus t by 2 x of t e power minus j k omega naught t dt. Correct? And it is always a good practice to compute a0 separately and compute ak for k not equals to 0. Okay, so instead of doing it in one go, always, okay, so there is no exception. I always suggest you do this in 2 steps. Compute for k is equals to 0. Okay, so this will be the first step. So if k is equals to 0, which means we are going after a0. And a0, remember, it's just the DC value of the signal, right? So a0 is the DC value. So if there is no 1 is 1 times e power j2 pi t into 0. So if there is any constant value that corresponds to a0, right? It is also the average value over a period, right? So this is also the average value over a period. Okay, so after computing also you'll see. So this a0, if you substitute k is equals to 0 in this particular analysis equation, you'll get 1 by t integral minus t by 2 to t by 2, and x of t will come there, x of t into e power minus j, k is 0, so omega naught t dt. So since k is 0 here, this whole term will just become 1. Right? So if the whole term becomes 1, the resultant would look like this. So 1 by t minus t by 2 to t by 2 x of t dt. So this is nothing but the average value, right? So, and we know from minus t by 2 to t by 2, if you see the signal, it is only non-zero, and the value is also 1. It is only non-zero from minus t1 to plus t1, and the value is 1. So therefore the integral limits will change from minus t1 to plus t1, and it will just be in that interval, it is 1 dt, and from minus t by 2 to minus t1 and t1 to t by 2, the signal is 0, integral of 0 is 0. You don't have to worry about. So if I simplify this will be 1 by t into, this is t, and the limits are t1 and minus t1. If you substitute and simplify it, you'll get 2 t1 by t, right? And this is a0. Right, so we have computed a0. which is 2t1 by t. And this is the average value also, you can check. If you compute the average value over a period, you will get that it is 2t1 by t. Now the second step would be compute AK for k not equals to 0. Okay, so now when k not equals to 0, AK expression would look like this: 1 by t minus t by 2 to t by 2 x of t e power minus j k omega naught t dt. Right, so here also the same thing. X of t is non-zero only in the interval minus t1 to plus t1, not from minus t by 2 to plus t by 2. So the integral limits will change from minus t by 2 to t by 2 to minus t1 to t1. And here x of t is 1 e power minus j k omega naught t dt. Right, so this is what it is. Then 1 by t. And if I integrate e power minus j k omega naught t, I'll get e power minus j k omega naught t divided by minus j k omega naught. Remember here the variable is t, small t, right? And the limits are t1 and minus t1. So all I have to do is I have to substitute capital T1 and minus capital T1 in place of small t. I will get 1 by t e power minus j k omega naught t1 divided by minus j k omega naught and minus e power minus j k omega naught minus t1 divided by minus j k omega naught. So we'll substitute omega naught also. Just be patient. Okay. So 1 by t. We'll just simplify some things. So here minus and minus, right? So this minus and this minus will become plus. And here also this will become plus. I'm going to write it as the first term now. E power j k omega naught t1 divided by j k omega naught. So I'll just do a marking. So I have written this term here and I'm going to write this term here. Okay, then plus, sorry, minus. So there is minus in the denominator, minus e power minus j k omega naught t1 divided by j k omega naught. Right, so this expression, the numerator, we know, we just saw that. So e power j k omega naught t1 minus e power minus j k omega naught t1, what will it be?
JK omega naught.
No, the numerator. So e power j theta minus e power minus j theta, where theta is k omega naught t1. So what will the resultant be in the numerator?
Sine
Sine
J K omega naught.
sine k omega naught t1. We are missing something.
2 sine.
Okay, 2 sine. Still we are missing something. Will it be 2 sine or 2j sine? What is e power j theta? Cos theta plus j sine theta, right? What is e power minus j theta? Cos theta minus j sine theta, right? So if I do the subtraction on both sides, the left hand side will be e power j theta minus e power minus j theta. On the right hand side, these two will get cancelled out. We will have 2j sine theta. So there will be 2j also in the picture divided by j k omega naught.
Okay, sir.
Right? So here there will be some cancellations. We'll just cancel them out. and substitute k omega naught is equals to 2 pi by t, right? So we just substitute omega is equals to 2 pi by t. This will give us 1 by t into 2 sine k 2 pi t1 by t divided by k into 2 pi by t. So now again, if you observe, this t and this t will get cancelled out.
2.
Right? Yeah, 2 and 2 will get cancelled out. Anything else? That's it, no? So we'll have the result to be this. Sine k 2 pi t1 by t whole divided by k pi. For k not equals to 0. Right? So that's the best thing I said, right? So if you computed this, then if you substitute k is equals to 0, it will go into 0 by 0 form, right? So sine 0 is 0 and even denominator is also 0. That doesn't make sense here, right? So you should also argue for k is equals to 0 case also. Okay. So there are some special cases where this capital T1 becomes this T by 4. So that's a special case, no? Exactly. Average value will be half. Right? So something like that. So this is some special case where our A naught will be half. You can compute. You can see 2 T1 by T, where T1 becomes T by 4. You will have a T and T gets cancelled out and 2 by 4 will be half. Right? So that will be A naught. And then you can also see AK will be sine k pi by 2. Right? You just substitute T by 4. T and T will get cancelled out. 2 and 4 will be cancelled out and 2 will be remained in the denominator. Sine k pi by 2 divided by k pi. And you can further simplify this because there is pi by 2 in the numerator, no? When k is even, can somebody comment on this? When k is even, what will be sine k pi by 2?
0, sir. 0, 0.
0. So this will be 0 when k is even. When k is odd, this will simply be k pi by 2 divided by k pi. So it will oscillate between +1 and -1, right? So when k is odd. So the numerator will be +1 once, -1 the other time. So, right? So this is the Fourier series coefficients for the special case. So this will be the Fourier series coefficient. And in general, these are the Fourier series coefficient, and this is how you should use the formula. Okay. All right. So any doubts in this from anyone? No? Should I move forward? All right. Nice. So the next thing is, as I mentioned, so not always you should sit and use those formulas. Okay. So you should not be blind. Like you should also use the techniques that you learn, right? So properties will help us to simplify and compute the Fourier series coefficients. So these are some nice properties, and these properties will also help you to cross check or validate your answers that you get. Right? So you would be in hurry and sometimes plus becomes minus and minus becomes plus. That is also acceptable, but sometimes complex number j becomes real number 1. Right? It should not happen, right? These kind of situations may happen, but you can cross validate and correct your answers if you know the properties. Okay, so these are some properties. that are listed here. We'll just go through it quickly. Right. So if your function is even, function I mean signal. Okay. So for every function I mean signal here. Okay. So if our signal is a even signal, then our Fourier series coefficients will also be even. They will be real and also even. So ak is equals to a minus k refers to that, right? So for k is equals to 1 and k is equals to minus 1, k is equals to 2 and k is equals to minus 2, all will be same. Okay, and they will also be real. And this we have done the example, right? So if you remember cos 2 pi t, so this is an even signal. Cos 2 pi t is an even signal. And if you remember, the coefficients that we got are a1 as half and a minus 1 as half. And everything else is 0. Here also you can see the coefficients are also even, right? And also they are real, right? Half and half, they are real. And the second property is if my signal is odd, and this also we have seen the example 1 plus sine 2 pi t, right? It's an odd signal. If it is odd, our a case will be imaginary, and again here also you can see k will not be 0. So you should exclude k being 0. So our a case will be imaginary, right? So this also we have seen. I think I forgot the values. A1 is 1 by 2j and a minus 1 is minus 1 by 2j, right? And there is a naught also, which is 1. Okay. So if my, sorry, 1 plus, sorry. Okay, if you 1 plus sine 2 pi t is not odd. Sorry, let me take that back. Sine 2 pi t is odd. So if you just compute sine 2 pi t's coefficients, you will not get a0, right? So if it is an odd function, a0 will be 0. That also you can say. A0 will always be 0 if it is an odd function. Okay, and all your AKs will be imaginary. You can see here also A1 and A minus 1 that we have computed. Both are imaginary and there will be a sign change, sign difference. So that means they are also odd. If it is an odd signal, my Fourier coefficients will also be odd. Okay, so like that, if my signal is real, then a minus k will be ak star, right? So if it is real, both the signals cos 2 pi t and sin 2 pi t are real signals. You can cross check. A1 is complex conjugate of a minus 1, right? Here also sin 2 pi t, 1 by 2j and minus 1 by 2j are complex conjugates to each other. So if it is a real signal, then our Fourier coefficients will be complex conjugates to each other. If it is a purely imaginary signal, so this we haven't done, but if it is purely imaginary signal, you can try it out. It will be antisymmetric or complex. It will be antisymmetric. Okay, CA, not CS. Okay, so it will be A minus Ks will be minus AK stars. All right, so these are the first four, and these combinations also you can look at. So what if it is even and real? If even and real, it will be real and symmetric. Odd and real is imaginary and antisymmetric. Even and imaginary is imaginary and symmetric. Odd and imaginary is real and antisymmetric. Okay, so why I said you can cross check is, so sometimes sin 2 pi t, if you try to compute the Fourier series coefficients, you might forget that j and think that the Fourier series coefficients are half and minus half. Okay, so in those situations, if you remember this property, then you will immediately get to know that whatever you have done is incorrect, right? So in that way, these properties will help. And the other thing is to simplify also. Okay, so there are few more properties which I would like to mention, and these properties will help us to compute Fourier series coefficients for some other signals, some other periodic signals, if they are connected to very well-known standard periodic signals. So some more properties of Fourier series we'll discuss. Okay, so far is it okay? Any doubts? No. If at all you have any doubts, you can unmute and ask. Okay, so that is always there. Let us continue. Yeah.
Sir, is there any properties for a function neither odd nor even?
No. So if it is neither even nor odd, is like it doesn't have any specialness in that. So there is
Okay,
no
sir.
such properties. Okay.
Okay, sir.
Yeah. So some more properties are, if I have some very well-known standard periodic signals Fourier coefficients. Okay, so if I know that, then can I compute Fourier series coefficients of some shifted version of it, or scaled version of it, or reversal version of it, or conjugate version of it. Right, so that is what I'm going to discuss now. So I'm going to write signal here and its corresponding Fourier coefficients. Okay, so if you know, so let's say this x of t is very special and we know Fourier series coefficients. Okay, some special or let's say standard. Let's not say some standard known signal, or it is given signal to us. It can also be the case. And you know that x of t's coefficients are ak. If you know this, then x of t plus, so let's discuss plus first. So if I shift it by some t naught units to the left, then the Fourier series coefficients will get multiplied by that amount, e power jk omega naught t naught. And you can, the beauty is it's not always formulas. Okay, so you should compute, right? So you just take the analysis function. Okay, so which I discussed, right? ak is equals to 1 by t integral minus t by 2. If you use that formula and try substituting, instead of t minus t plus t naught, you just take it as u, right? So then do some manipulations and you will see. It is good to prove. Okay, so once you prove it, you will remember it. Okay. I think I feel like I shouldn't do it. Maybe you guys can try it out, and it can be proven. That is what my conclusion is. It's not it doesn't came from there is no magic behind this. Okay, so there is math behind this. Okay, so if it is minus, then here it would be minus. Okay, so if it is shifted to the left, then you will get multiplied by e power jk omega naught t naught. If it is shifted to the right, then it will get multiplied by e power minus jk omega naught t naught. So this is with respect to shifting. Okay, and if it is reversal, it is like x of minus t, then the Fourier series will just become a minus k. They will also go reversal. So a1 becomes a minus 1, a minus 1 becomes a1, a2 becomes a minus 2, a minus 2 becomes a2, like that. Okay, so if you do the reversal of our signal, here also the coefficients will get reversed. Again, this also you can prove, and you can prove this easily using the synthesis equation, the first equation. X of t is equals to summation we have, right? In place of t, you replace minus t, and all your coefficients will get interchanged. Your k will become minus k. Okay, so this is with respect to reversal. And the next comes is the scaling. So this will be slightly confusing, but let's try to remove that confusion. So it can be represented in two ways, but the most followed by many of the books is this way. So the Fourier series coefficients will not change. Okay, so even if you scale, the Fourier series coefficients will not change. Scaling will affect on the frequency. Okay, so the fundamental frequency will change to some omega prime, which will be c times omega naught. Okay, again, this also you can prove using synthesis equations. You just take x of ct in your synthesis equation and you club. So maybe this is very easy to show, I guess. So x of ct will simply be summation k is equals to minus infinite to plus infinite ak into e power j k omega naught ct, right? So what you do is ak e power j k c omega naught t, right? So the frequency now the fundamental frequency will be c omega naught. This t is t, this j is j, and ak will be the kth harmonic sinusoids coefficient. So the Fourier series coefficients won't change, but you should be careful that fundamental frequency will change. Okay, and yeah, I think the other version professor has also discussed, which will be Fourier series will get updated to k by c. Right, so that is also there, but you can follow this alone instead of looking into two different things. You can just simply follow that scaling doesn't affect the Fourier series coefficients. Okay, and the next thing is what happens if I take the conjugate of my signal, right? So what will be the Fourier series coefficients of x star of t? So the conjugate will become a star minus k. Okay, and again, this also you can prove it using the synthesis equation. Okay, so if x of t is real, okay, as I mentioned, it's a special case, right? So if x of t is real, right? So conjugation doesn't, it's redundant, right? So x of t will be equals to x star of t, which implies that your ak is equals to a minus k star. And if you just scroll a bit above, if it is real, a minus k is equals to ak star, or you can rewrite it as ak will be equals to a minus k star. Okay, so that is one more property. Okay, only if x of t is real, right? So yeah, I think these are some properties, and linearity. Yeah, I forgot that. So if you have two signals, okay, x of t which has some, we'll represent it like this. Okay, so fs, we'll just put fs on top, which says that it's a pair. X of t and ak are pair. X of t is the signal, ak are Fourier series coefficient, and some y of t, and its Fourier series coefficient is some bk. Then the linear combination of these two signals, alpha times x of t plus beta times y of t. This signal's Fourier series coefficient is alpha ak plus beta bk. And this also you can prove using analysis equation. Okay, so either one of it you can use it, and you can prove every property that I mentioned here in 2 steps, 2 or 3 steps at max. Okay. So yeah, I think with that, I think professor has closed week 7. So with these properties, we have closed. And in week 8, we started talking about the multiplication of. So that is also there. So when x of t gets multiplied with y of t, what happens to the Fourier series coefficients? And unfortunately, it will be the convolution which we all get confused, right? So yeah. So that's about week 7 majorly. Okay, so some interesting discussion is happening in the chat, I guess. Okay. Do we need to learn the proof? So you don't need to learn the proofs, but yeah, as Nanda mentioned, it will give you better understanding. Yeah. So yeah, as I mentioned, no, if you prove it, then you won't forget it. Like there is high chance that you won't forget it. I'm not saying you won't forget, but once you prove, no, you will understand it better. Okay, so that's the thing. All right, so I think that's all I wanted to discuss. If you guys have any doubts, we can discuss. And few announcements. This Saturday we are going to do the third MATLAB session. Okay, so it is related to the third exercise, simulation exercise in your MATLAB. And I saw there is some like 60% of the people have attempted, 60 to 65% people have attempted simulation exercise 1 and simulation exercise 2, which we didn't expect. Like we expected more. I don't know what happened to the rest 35% people who didn't even come to MATLAB, or we have no answers from our side. Like, is it too difficult, or what is going? Is the information is not sent properly? Is there anyone still in this particular meet who doesn't know this lab exercise thing which is happening parallelly along with the course? No, right? So we have given enough reminders in the G space. Even in the live sessions also we were discussing about it. So I don't know. 35% is very huge. And also that MATLAB has 10% of weightage. Okay. Oh. Yeah, so even if you miss the first two things, all I suggest is at least start from third. There are 3 more coming, 3, 4, 5, 2 more coming. Okay, so at least you solve and submit 3, 4, 5. You'll get some 7, 8 marks out of 10, and 7 marks at least. Okay, so that's one thing. And the next thing is we really don't have time for quiz 2. Okay, so you should all speed up your preparations. Okay, and I put the deadline as 5th June. It should be 5th August, no? Yeah. I was confused. I thought I gave 5th June as the deadline. Okay, so 5th August is the deadline for third assignment, because 3rd August is the quiz 2 exam, and I felt as of now we have very less time to prepare for quiz 2. If I put the deadline before the exam, it won't be really nice. So that is why I put the deadline as 5th August, so that you give 3rd August exam first. Then you have 2 long days to submit simulation exercise 3. Okay. So coming back to quiz 2 thing. So quiz 1, I don't know how you guys felt. I am really unhappy with the quiz 1 result. because I expected a lot of you will get very good scores, which didn't happen. And on top of it, we don't have too much time to prepare for quiz 2 also. So all I suggest is let's speed this up. If you are still in week 6, finish week 6 as early as possible and come to week 7. So week 7 and week 8 are interconnected, which completely focuses on Fourier series. So if you are stuck with this LTI systems and some circuits which are coming in, right? So if you are not okay with that, then I will suggest that just leave that aside for now. Start week 7, finish week 7 and week 8 as quickly as possible. Then during revision sessions we will anyway cover week 5, 6, 7, 8. So in that your week 6 will get revised. Okay. So this time we will prepare better, and I really expect quiz 2 goes really well, so that we can take some breather after quiz 2 and then start preparing for enter.
Sir,
Okay. Yeah.
sir, what is the syllabus for week two, quiz 2? Week
It
5
is
to 8 or 1 to 8?
5 to 8. 5 to 8.
Okay, sir.
Okay. So that is why I'm telling you there are only 4 weeks, but time is also very less. So you have to be like you have to know the techniques to prepare for the exam.
Sir, there will be no questions from 1 to 4, sir.
No. Do you
Only
want?
from week 5 to week 8.
Yeah, only from week 5 to week 8. But if you guys want, we can add.
No, sir. No,
No?
sir.
Hello, sir.
Okay. Yeah.
So I'm facing problem in MATLAB sessions by the TA. So it's hard to understand what he's saying. So maybe it's specific problem to myself, but I'm can't able to understand.
Sorry. The last statement I missed.
So I can't able to understand what
Yeah, I got that. Okay, so we'll do something about it then. Okay.
Okay, sir. Okay, sir.
Okay, so we'll see. Let this Saturday happen. Okay, so we can't change this Saturday. Maybe after August 3rd, no? The deadline is on August 5th, right? So maybe on
Yes,
August
sir.
4th, one of the instructor session, we kind of spend some time on simulation exercise 3 once again. Okay, so let this Saturday go. Then hey, what kind of discussion is happening here? Oh, who will lose her? Nanda? Oh. And somebody suggesting some oil within no time. Oh my god. You guys are crazy. Okay, anyway, if no doubts, then we can formally end the session here so that both of our times can be used in some other thing. Okay, so I'm stopping
Yeah,
the
thank you,
stream
sir.
here. Yeah. Okay, guys.
Thank you,
Thanks a
sir.
lot. And